In the last video, we talked about optimization problems, where we wanted to consider a real-life situation where there's some variable that changes, and we want to find the value of that changeable variable that will either maximize or minimize some function. And that obviously there are a zillion real world situations where this is going to be important. Sometimes it's a complicated situation and you'll need to be told what that function is, or you'll need to use statistical analysis or something in the real world to figure out what that function is. Sometimes it's something we'll be able to calculate the function ourselves. Let's take a look at that second type where we can calculate the function that we need to optimize ourselves. So this will be a little bit of a geometry problem. So a farmer has 400 yards of fencing and wishes to fence 3 sides of a rectangular field. So the fourth side is a stone wall which already exists. So we only need to use the fencing for 3 sides in order to enclose the area. So we want to figure out how to do that in such a way that we're using the 400 yards of fencing and we're enclosing the largest area we possibly can. So one thing I love to do when we start a situation like this is I like to make a drawing of the thing that's going on. So my stone wall will look something like that. And these are the 3 parts of fencing that we're putting in. Okay, so how long are these 3 sides? Well, I don't know. So let me just say that this is the one we have control over. So I can control the width. So that'll be X. And this is a rectangle. So this side's also going to be X. What's the length of this rectangle based on the information we have in this problem? Well, we have 400 yards of fencing in all that we're going to use. We've used X to make this wall and X to make this wall. So that leaves us with 400 minus 2x to be used for the length of the wall. Okay, and now that we've built this wall out of these 3 pieces of fencing, how do we calculate the area of the fence? Well, this is a rectangle, so the area, and this is a function of x, the area depends on what value of x we chose here, is equal to the length times the width of the rectangle. So that would be x times 400 minus 2x. So we could write that as 400x minus 2x squared. So now that we've got this situation, we kind of can take this whole thing and turn it into something that looks like a calculus problem. Because what we want to do is we want to find the maximum, let's say the global maximum of A. Okay, we want to calculate the value of x that makes the largest possible value here, because that's going to tell us the width of the rectangle that gives us the largest area. So how have we been finding the maximum value of a function up to this point? Well, what we want to do is we want to take the derivative of A. So the derivative of 400x is 400. The derivative of negative 2x squared is minus 4x. And we want to see what value of this gives us a derivative of 0. 400 minus 4x is equal to 0. So what value of x gives us this critical point? All right, so we're going to add 4x to both sides. So 400 is equal to 4x. Divide both sides by 4, and we get x equals 100. Okay, so this gives us a value of the function, but off the top of our heads, we're not 100% sure whether this is a maximum or a minimum value, or whether it's neither. Okay, so in this case, let's use the second derivative rule just to test. So we've calculated that a prime of x is equal to 400 minus 4x. So the second derivative of the area is equal to what? 400 is a constant, that goes away. Negative 4x, the derivative is just negative 4. So the second derivative is negative everywhere. No matter what x is, the second derivative is negative. So that means that around this point, it's going to be concave down. So the function is going to look something like that. So this is, in fact, a maximum value. And since it's concave down everywhere, it's the only maximum value. So this must be our global maximum. Okay, so let's make sure we answer the question. We want to find the dimensions of the rectangular field of largest area that can be fenced. So x is equal to 100. So this should be 100 yards in width. And what's the length going to be? Well, 400 minus 2 times 100 is 400 minus 200, which is 200 yards. All right, so 100 yards by 200 yards is the largest possible rectangle. And if we wanted, we could calculate that. So that would be 20,000 square yards would be the area of it, which we can get either by multiplying these two things or by plugging 100 into the area function right there. Okay, so that gives you an idea of how to solve an optimization problem. So there are a couple steps. The first thing we need to do is we need to calculate the function that we need to optimize. So I drew a little diagram there, and that helped me calculate that. And then based on that function that we come up with, we want to find the maximum or the minimum value, which we do the way we've been doing up to this point, by taking the first derivative, setting that equal to 0, and then for any answers that come out, checking to make sure that it is either the maximum or minimum value that we're interested in by using either the first derivative rule or the second derivative rule.